Hello, everyone. Welcome to today's webinar on Stop the Spread, Improving Indoor Air Quality Using UV Air Disinfection. Thanks for joining us today. I'm Ann Cosgrove, the Editor-in-Chief of Facility Executive Magazine, and this webinar is presented by Heraeus Noble Light America. Before we get started, I would like to cover a few housekeeping items. Please note the control panel on your screen. This is where you can submit questions in the question box in that panel. We will be doing a Q&A at the end with your speaker. You can send your questions in at any time and they'll be addressed after the presentation. Also, please note the orange arrow on the left side of the control panel. Clicking on that will either expand or collapse it, so please be sure it is expanded. Also, if you experience a technical difficulty or have a non-content related question, you can also send our staff the question there and someone will answer you privately. If you're interested in a continuing education credit for this session, please note you'll receive a certificate of attendance in an email from Facility Executive after this webinar, and you can report that to your association. Now, moving along, I'd like to introduce today's speaker, Eric Nelson. Eric is an environmental application engineer with Heraeus Noble Light. He has spent the last 5 years managing the company's application testing lab in Gaithersburg, Maryland, conducting customer trials and evaluating UV technologies. His experience includes the measurement and operation of UV systems and processes, analysis of UV reactive chemistries and materials, and design of UV curing and disinfection systems. Eric provides technical consultations for testing, design, and specification of UVC air disinfection solutions, and he holds a bachelor's degree in materials science and engineering from Alfred University and environmental policy and law from Binghamton University. So we're looking forward to a good discussion from Eric today, and also, of course, your questions toward the end. Hi, Eric. Thanks for joining us.
Hi, Ann. Thank you. And hello, everyone. Thank you for joining. Well, let's move right into the agenda for today's presentation. I'll start off with a little bit of a talk about what is UV energy. And then I'm going to discuss a little bit about the history of UV for disinfection. Then I'm going to go a little deeper into the science of UV disinfection, go over how it works, where it works. Then I'll give some technology examples of different UV systems. And then we'll go over, mixed in there, a few different case studies of UV technology being used in the real world. But first, we're going to have a little polling question for everyone.
Yes, thank you, Eric. So everyone, you should be seeing the poll on your screen. And if you can take a moment to check all that apply to this question. And the question is, what steps have you taken to prevent the spread of COVID-19 pathogens and variants, flu, and other viruses in your facilities? Can you please check all that apply? You'll see the choices there are mask wearing, social distancing, remote work policies. The second is increased ventilation. The third is installed higher MERV or HEPA filters in your HVAC. That fourth is portable air purifiers in high occupancy areas. And that last selection is installed air purification device in ventilation system. So please go ahead and check all that apply. We will show the results very shortly once we get some critical mass on the votes, and we will show those on the screen. Okay, so let's see. Okay, so 55% mask wearing, social distancing, remote work policies. So over half are incorporating those, have incorporated those, followed by 18% installed higher MERV or HEPA filters, 12% increased ventilation, and followed by air purifiers and hair purification devices in ventilation. So thank you very much. And I'm seeing here we're only able to choose one choice. So just to clarify that, in only being able to choose one, 55% chose that top mask wearing, social distancing, remote. Thanks again, everyone. I'll hand it back to you, Eric.
Thank you. And we'll have one other polling question later on in the presentation. But I think, to prevent the spread of COVID, the best course of action is to take a layered approach, probably with multiple methods, and that's kind of what we're going to be talking about today. But first, let's start by taking a little look at the electromagnetic spectrum, which some of you are hopefully familiar with. For those who need a refresher, all forms of energy, from X-rays to visible light to radio waves, travel through space in the form of a wave. Not only that, but each kind of energy is expressed through a specific size of wave. So longer wavelength energy, such as radio waves, can be meters long, whereas visible light travels in waves that are only a few hundred nanometers long. In physics, we use the lambda term to describe the size or length of a single wave of energy. So, and then we use the term V to describe the frequency. So very short wavelengths have a very high frequency since each wave is pushed up extremely tightly next to each other. And by using Planck's law, E equals hv, with the Planck's constant, we can see that higher frequency or shorter wavelength energy is more energetic than long wavelength energy. So now let's take a look at the spectrum itself. In the visible region, we see the rainbow of visible colors. These range in wavelengths from around 400 nanometers up to around 800 nanometers. Red is about 780 nanometers. Yellow light is around 600 nanometers long. And then as we go lower, we move into the blue and then the violet. And beyond the violet color in the visible spectrum, we reach the ultraviolet region of energy. And just like visible light, each wavelength is associated with different properties and produces unique material interactions. So higher wavelength UV energy, we refer to as UVA. This is the UV energy most commonly associated with sunlight for us on the surface of the Earth. UVA lamps are commonly used for the UV curing industry, where UV energy is used to dry inks, coatings, and adhesives at high speeds. It's also used in sun tanning. Moving down to the UVB region, we see these wavelengths commonly used for UV curing, but also in different medical applications. And finally, lower, we have UVC. This is the region that produces the disinfecting energy that we're going to be talking about today. And if you get even lower, we get to the vacuum UV section, where UV energy is actually not able to transmit on the surface of the Earth because it's absorbed by the air in the atmosphere. So now let's take a quick look at the history of UV disinfection. UV disinfection was first discovered and noted in 1877 by British physiologist Arthur Downes and scientist Thomas P. Blunt. They observed sunlight inactivating bacteria in water. And within just a couple decades, by 1903, Niels Ryberg-Finsen wins the Nobel Prize in Medicine for the use of UV energy to treat skin diseases. And at this point in time, they were using a combination of sunlight and also artificial light, which was produced by carbon filaments and crystals to focus the energy. 1 year later, in 1904, Heraeus invented the first quartz glass lamp. And this is still the primary technology used to generate UV energy today. And we at Heraeus still make these lamps today. By the 1930s, studies were being conducted. For example, this is a study by William F. Wells, who was a sanitary engineer from Harvard University. And he installed UV lamps into the upper air regions of a classroom to prevent the spread of measles. And what they found was just by having these static UV lamps sitting above a classroom setting, measles infection rates dropped from 53.6% to 13.3%. Now let's take a closer look at the Mercury Arc Lamp, which is the most commonly used lamp for disinfection. How these lamps work is there's an electrical current that's used to strike an arc between two electrodes. And this arc of electrons is sometimes referred to as an electron avalanche. And when that begins to move through a enclosed environment, it excites the mercury and that's enclosed inside. And the mercury, which is sealed into this vacuum tube, along with inert gases such as argon, generate a UV emitting plasma, which emits high energy UV. Now I've mentioned that the quartz lamp was invented by Heraeus over 100 years ago. What is quartz in this context? Quartz is actually a term used to describe high quality, high purity silica glass. And it's used because of its very high transmissivity of low wavelength energy. So we see some energy curves down here. This is different kinds of glass, and there are different properties at being able to transmit different UV wavelengths. So in UV energy, many, the most common type of lamp is a Mercury style lamp, and it's actually very similar to a fluorescent style lamp, with the grade of glass being the primary difference. And if everything is balanced correctly in terms of air pressure and chemical mixture inside of the bulb, the Mercury lamp will produce a very large spike at 254 nanometers. And this is the wavelength most commonly used for disinfection applications today. So today we see a very wide range of 254 nanometer disinfection applications, everywhere from the healthcare industry, where it's used to treat the air and also treat surfaces of hospital rooms and care rooms, to the treatment of drinking water and processed water and wastewater. We see it used in air handling systems for air treatment in large spaces such as airports, offices, and other communal areas. And it's also used in the disinfection of food and food packaging. So going a little bit deeper into these different areas of application, UV water treatment is very common and the longest used application for UVC disinfection. And today it's used everywhere from the beverage industry, where it's used to purify water, to aquaculture and agriculture, to keep the water clean and prevent the spread of bacteria. It's also used to treat Legionella, which spreads through water vapors in the air, treats swimming pools. A new application is ballast water treatment. So large cargo ships traveling across the ocean, when they reach their final destination, before they unload or release any water into this new environment, they now have to treat their water with UV. It's also used very widely in wastewater disinfection and for drinking water. Next is surface disinfection. UV is ideal for disinfecting the surfaces of food and food packaging. It removes any harmful microbes that are on the surface of these food products and prevents these bacteria from infecting whoever eats them or whoever uses them to pack the food inside of. A common application for surface disinfection would be the disinfection of empty yogurt cups before they're filled. So simply by irradiating an empty cup with UV energy, we're able to extend the shelf life by about 2 weeks. Lastly, we have the focus of today's talk, which is UVC air treatment. UV has a long history of being installed in air ducts and air handling systems, where it's used to improve air quality, prevent germs and allergens from entering buildings, purify exhaust air and removing odor, breaking down different kinds of particulates, such as in kitchen hoods, where UV lamps are installed in the exhaust air to break down smoke, grease, and odors. It can treat input air in entering a building, or it can treat recirculated air. And the high intensity UV energy treats microbes directly, disinfects them immediately, so there's no need for any kind of chemical cleaning or use of filters. So now that I've gone over a little more about what UV energy is and where it's used, let's talk about the science of UV disinfection. So in order to produce a germicidal effect in a virus or other microbe, a certain amount of UV energy is required. We use the term dose to describe the total amount of energy absorbed over a given area. Dose is a function of both power and time, with a low amount of energy being absorbed over a long period of time being equal to a high amount of energy absorbed over a short period of time. And what we've found is that once a minimum UV dose is reached, the disinfection of a given microbe will occur. So the higher the dose, the greater the level of disinfection. And the UV dose that's required to disinfect any given microbe is completely unique and predictable. So this means that we know how much energy is required to disinfect SARS-CoV-2, and we know how much is required to disinfect the flu. So to give you an idea of how much dose is required to disinfect different microbes, we can look at the chart here. And there are also much larger databases comparing UV sensitivities for pretty much every known microbe that we know of. So in the medical industry, there's a lot of discussion about antibiotic-resistant bacteria, where over many years of using antibiotics to treat illnesses, some bacteria have evolved a resistance. This is not the case with UV, and as of right now, there's actually no known UV-resistant viruses or bacteria. In fact, all known microbes are susceptible to UV radiation, with viruses and bacteria being the least resistant, while molds and spores being flora with slightly thicker cell walls require typically slightly more energy to disinfect. So all microbes are sensitive to UV energy, but how much of the 254 nanometer energy produced by a mercury lamp actually affects these microbes? UVC energy produced by our sun is actually blocked out by the Earth's atmosphere, which means that cells have evolved without ever needing to interact with this kind of energy. And in fact, we find that these wavelengths are easily absorbed by DNA, which causes mutations to occur. A mutation in the nucleotide, this link here between the DNA strands, it inactivates a single cellular microbe, and that makes it unable to reproduce or spread if it infects a host. So fortunately, the 254 nanometer output of the mercury lamp aligns very well with the absorption spectra of most common microbes, and this is what makes it so suitable for UVC disinfection. So this breaking of the nucleotide chain is called dimerization, and yeah, you might have guessed it works on SARS-CoV-2 as well. And this has been scientifically proven at this point. There have been a number of different studies testing the disinfection of COVID in different environments, whether it be in the air or on surfaces. We've internally done many tests with third-party labs, and we've also seen many studies globally coming out that show the ability for UV to disinfect. And when we're talking about COVID, really what we're talking about is the risk of infections traveling through the air, and specifically aerosolized COVID traveling through the air. So in 2021, the CDC published an article stating that the principal mode by which people are infected with SARS-CoV-2 is through the exposure to respiratory fluids carrying the infectious virus. And just a couple of weeks ago, the University of Cambridge actually published a report showing that in a healthcare setting, mask wearing reduces the number of COVID cases, and it reduced the cases in their trial from 14.3 to 4.3 cases per week. So really anything we can do to prevent these aerosols from being in the air and from freely traveling from person to person is our best means of preventing the spread of COVID. And to reduce the risk of infection as much as possible, we need to really have a layered approach. There's a few different routes by which COVID can spread to people, most notably surface contamination, aerosolized particles in the air, and direct transmission. Surface contamination can be treated by washing hands, cleaning surfaces, and direct transmission can be avoided by socially distancing and wearing masks. But how do we treat the aerosolized particles? This is where UV comes into play. We need some kind of active means of reducing the virus. Now, in an earlier slide, I showed that picture of an upper room UV unit being used in the 1930s to prevent the spread of measles. Well, this technology has actually advanced quite a bit in the last 90 years. Aside from being much more intense and electrically efficient, these lamps are also able to operate for much longer periods of time. And we're now able to integrate different designs and processes into the lamps themselves. So for example, this is a UV system which has an integrated fan system built into it. And this allows us to maximize the amount of airflow through the UV zone. And what we see here is an example of a UV disinfection system where microbes are pulled into a closed UV chamber, then disinfected with a high UV dose, and then recirculated back into the room as clean air. COVID-19 has had a serious impact for workers in every industry. Here are the results from a study from the UK, which showed that a percentage of workers from every profession, ranging from nurses to taxi drivers to accountants, has seen an impact from COVID mortality. And of course, professions with the greatest amount of public interaction have the greatest level of risk. But what this data makes clear is that an active mitigation practice is needed to improve safety and prevent workplace disruptions in really every industry. And I believe we have a second polling question now.
Yes, hi Eric, it's Ann, we do. Okay, and everyone, you should see that on your screen. We'd like to ask you to select one of the following here. And we'd just like to know, what's the primary reason you want to reduce the threat of infectious aerosols in your building at this point in time? What's the primary reason? Protect buildings for occupants from illness, prevent business disruptions and closings, ensure occupants feel safe in the building, or to help prevent community spread of viruses? So which one's that primary concern of yours at this point? And then we will show the results as we did with the first one. Thank you. Okay, so we should be showing that momentarily. And let's see, 49%, about half, protect building occupants from illness. So there you go, Eric. That was followed 27%, ensure occupants feel safe. Then 15%, prevent business disruptions. Rounds it out 10%, the community spread concern. So thanks again, everybody. Back to you, Eric.
Great, thank you. And yeah, UV is a great means of doing this, improving safety at a workplace. And now we're going to go over a little more specifically about different UV systems and the different designs and means that we're incorporating to address these problems. So let's go over the UV advantage. Why use UV as a technology for combating COVID rather than a different technology? Well, one major advantage is the flexibility of designs. UV systems are available as a complete system or as a retrofit. We see here an example of a freestanding wall-mounted UV unit, but they can also be integrated into an existing ductwork. UV systems can be used to disinfect any size space, including individual rooms or entire buildings, depending on the requirements. UV energy is able to treat all kinds of microbes, like I mentioned earlier, including bacteria, viruses, molds, and spores. Some other forms of air treatment technology, such as filters, might only be able to filter out larger particulates while allowing smaller viruses to pass through. Other technologies might only capture the extremely small particles while not really having an effect on large allergens or molds. UV handles everything. UV is able to treat the air with no chemicals or filters required. What does this mean? Well, we can save on supplies and maintenance costs. There's basically just a couple, 1 or 2 UV bulbs inside of a system, and they typically last for a year or more before you have to change it out. You don't have to, if you install it into an existing system, such as an existing air handling system, there's no real change in operation of the air handling system. You're not adding any sort of filters that would block or restrict the airflow. So it's an easy retrofit process that doesn't really change any building maintenance practices. And also there's no harmful byproducts. All that we really use is a UV bulb. And when it's used up, you can recycle it like any other fluorescent light bulb. In the case of a filtered system, the filter is going to be capturing all sorts of viruses and molds and holding on everything inside of it, so it sort of becomes a hazardous waste byproduct at the end of its lifetime. And of course, UV is extremely fast and efficient. To disinfect COVID from a high intensity UV source, you would only need a second or a fraction of a second in order to reach a very high level of inactivation and disinfection. And UV is a proven technology. For over 100 years, UV has been used for disinfection, and it's very well understood how it affects different microbes and different organisms. Now let's quickly go over some UV safety information. Just like UV is harmful to microbes, I do want to mention that UV energy is also harmful, and it's a hazard for human beings. The greatest risk for people is typically skin or eye exposure, which is why we recommend avoiding direct skin or eye contact. And this can be done by installing a complete system like I showed earlier. It can also be done by installing into a duct system, which is in itself a closed system. And also you should choose a design that has some kind of safety interlock set up so that the UV lamp can't be accidentally exposed to anyone working nearby it. It's also important to choose the correct lamp. You want a high power system so that you don't have any kind of dust buildup on the bulb. If it's extremely low power, it could be some kind of fire risk or something like that. You also want to get a long life bulb so that you have a really stable output and predictable output, so you know how much the system is doing and what it's performing. And these UV lamps can come as ozone generators or as an ozone-free lamp. And ozone is a hazard to humans to breathe, so you'll definitely want to select the correct system for your given application there. Now here's an example of a wall-mounted unit that we're making. We call it the Soluva Air W. This is a unit that can be mounted onto the wall in an office building, in a conference room. We have a couple of these scattered throughout our office, in our lobby, in our break room. And I can honestly say that having a UV system in our conference room makes it a room, in one of our conference rooms, makes it the conference room that everyone wants to go to. These units can be mounted onto a wall, or they can be put on a TV stand and move from room to room as needed. They're a very flexible option. They're best in smaller spaces or medium-sized spaces, and we have done testing to prove their efficacy against COVID. And here's an example of a test that we ran. This is actually a trial that we had performed at a third-party lab in Germany, known as the Fraunhofer Institute. And what they did was set up these test dummies in a simulated classroom environment. And these dummies had an aerosolizer installed near their mouths. So they actually emitted a measured amount of a COVID surrogate virus at a rate equal to, or equivalent to human respiration. And so what we did was the virus was emitted for about 80 minutes, and then the Soluva W was turned on and started treating the air. And what we found was that after 45 minutes of operation, over half of the virus was detectable. Less than half of the virus was detectable. So simply by having a UV system operating, you can already reduce the infection by over 50%. And after 160 minutes, so this is after the virus was no longer emitted for 10 minutes and the UV system operated on its own for 10 minutes, now we're up to 98% of all viruses removed. So if it comes to a matter of cleaning out a space after people have left, UV is also a great option for that. And after 20 minutes, we have over 99% of virus disinfected. Now here's a case study from France, which showed the importance of having some kind of air treatment system installed in a school or really in any building. What they found was that they had a really wide-ranging study from 677 different schools, and what they saw was that in schools that had no air purifiers, there were 6.8 cases of COVID detected. And in cases where schools had some kind of air filtration or air purifier installed, the number of infections were down to 1.8. Now here's another design for a different kind of UV system. I mentioned this briefly earlier, but UV can be installed into an existing duct system in a building, or it can be installed into a new ventilation system being built in a new building. Basically what we do is utilize the existing infrastructure to circulate the air because there's already an airflow passing through here. And it's also a closed system, so there's no risk of UV light leaking out. And these systems can be designed these are built for all different sizes ducts, different lengths they can come in, and it's fully stackable to treat any air volume. So, going back to what we discussed earlier with UV dose, there's a given UV dose required to disinfect COVID. If you have an extremely high flow air handling system that's pushing huge volumes of air past the lamps extremely quickly, you can simply stack two of these lamps side by side, double the dose, double the effectiveness of the UV system. And here's some technical details of the duct, which we're calling the Air D, Soluva D. Well, a single system can disinfect 500 CFM of air with an air velocity of 50 feet per minute. These have 2 bulbs on them, and these bulbs are expected to last about 9,000 hours. So we would recommend changing these out about once a year. They're available in 4 different lengths, ranging from 14 to 32 inches. And we are currently in the UL approval and testing process. So when we release these to the US market, they will be UL approved. Now here's another case of a super spreader event that occurred in China back in 2020. Over a 50-minute long bus ride, 35% of all passengers on a bus became infected with SARS-CoV-2. And it's believed that the air conditioning system may have aided in the distribution of the virus in this case. What's a possible solution for treating a virus like this? Well, it would be to install a UV system into the bus itself. And you can see on the right here is a picture of one such system possibility. And this is a new system that we're coming out with. It's called the Soluva V for vehicle. And it can be mounted into the ceiling of all different kinds of vehicles, everything from trains to buses, vans, corporate shuttles, RVs, really anything at all. It operates on 12 volts. It's very easy to install. You just screw it into the roof. And just by having this UV chamber, disinfecting the air in a bus, you can significantly reduce the risk for both the drivers and the passengers inside the vehicle. And here's another new product that we're coming out with soon. This is the Soluva T, or Tabletop Design. This is a desktop type device, which is extremely small and compact. And the concept here is you place a UV disinfection chamber on top of a conference room table, or in an office or meeting room, in a reception area, or really any shared space. And anyone sitting around the table would have the air disinfected as they breathe it out. So greatly improving the safety for everyone that would be inside of these small enclosed spaces. So to summarize, UV is a scalable technology for many different spaces and applications. It treats the air without the use of chemicals or filters. It fully inactivates all known viruses. It doesn't just capture them. And complete systems are easy to install and operate with pretty low maintenance costs and high reliability. So I'll now take some questions.
Okay, awesome. Thank you, Eric. Thanks for that overview. We do have some questions, so we will go through these now. Okay, so let's see. I'm going to start with a question about actual sizing this for a facility, and this is specifically for the induct products or the induct system. And the question generally is, so how many of your lamps would be required for an induct system? And I realize that's very general, but perhaps you could give us some context in terms of an actual building installation and kind of, figuring out how many units need to go in if you're looking at your HVAC ducting system. How does that work?
Absolutely. Well, so we have a scalable solution for any, required amount of air volume. But typically what we're targeting with these kinds of systems with our Soluva duct unit is recirculated air, because this is the highest risk of containing the COVID virus in it. Basically, any air that people are breathing out in the building that gets recirculated back into the airstream is much higher risk than air coming from the outside. So typically, these airstreams have a slightly lower airflow rate than input air coming from the outside, which means that it's pretty easy to treat this sort of air with probably just one of these units installed. That said, I mentioned earlier that we're really calculating these units and specifying them for specific cases. So if you have a case where you're over 500 CFM and you have an extremely large duct, you might need 2 of these systems back to back. But basically our goal is to get about 1 second of time inside of a highly energetic UV field, and that's enough to produce typically enough energy to disinfect COVID. I didn't mention this previously in the talk, but the common number that's used right now as a reference for disinfecting COVID is about 15 millijoules per centimeter squared, which we can achieve pretty quickly in one of these kinds of systems.
Okay, thank you. Thanks for that. And of course, anyone in the audience, please do continue to send in your questions as we talk about these topics here, if anything comes to mind as we move through here. So Eric, I'm going to stick with the theme of operation because you had just kind of talked about the operation a bit. And the question I had here is, can you talk about the power requirement of the units? And I'm going to stick here with an induct unit. Of course, if you want to kind of move out of that, let's just be clear on which products we're talking about. But a power requirement is the question. Is there a heat output that is a concern? Can you talk about that power requirement as well as any heat output?
Yeah, well, the lamps themselves operate at a pretty cool temperature. There is an ideal operating range, which I believe is about 30 to 80 degrees Fahrenheit. So the efficiency or the output will drop off slightly if you fall outside that window of air temperatures. In terms of electrical requirements, these systems that we're making are designed to just work on any kind of common wall plug. So quite easy to power and operate.
Okay, thank you. And I'm just going to ask you one more question along that line. Another one just came in about the operation. Do these products, these cleaners, the UV cleaners, how much noise do they produce is basically the question. Is there a noticeable noise, anything like that we should know about?
Well, it depends on the system. The extremely large system might generate some noise from a fan spinning, but it's scalable to any setting. So, like the tabletop unit that I was showing earlier, those are extremely quiet. You can barely hear it. A wall-mounted unit, you can operate it at a lower setting and it's basically silent, or you can really crank it up and it's a little louder. But if you don't want that kind of noise pollution, you could always put 2 units in a room and you would need half the airflow. Yeah, they're pretty quiet and pretty easy to operate.
Okay, thank you. Okay, and I'm going to move to another question here about operation. Could you talk about the question is how many air changes per hour are achieved with a typical in-room air cleaner installation? Is that something that you can speak to?
Yeah, well, I'll say a few things about that. First of all, air exchanges is really what we're going for, right? So in a hospital, they have something like 9 air exchanges per hour, and that's considered to be a safe level for a really dangerous healthcare kind of environment. Typically, if we're sizing a room, we're trying to specify a system to fit in a certain room, we like to have about 3 air exchanges per hour. Just as a safety factor. A lot of the studies we've done have shown that this kind of reduces the risk of infection by over 50%, just having 3 air exchanges per hour. That said, some of the smaller, more targeted units, like a tabletop unit, probably wouldn't be able to exchange the air in the entire room. But if you're really concentrating on the highest risk areas, such as the area between 2 people that are speaking, you probably need a slightly lower flow rate to really treat that air.
Okay, thank you. And then I'm gonna circle around that before moving on, and I want to ask you, what's the typical operating life of the UV lamp, the UV unit, I should say? And let's stay with the induct, unless you want to expand, of course. But I just
Yeah.
want to be clear what we're talking about. Typical operating life, and you've talked a little bit about maintenance, but is there anything else you can talk about there that folks might need to know about the actual maintenance once it's in place?
Sure, yeah. So our duct system is designed to last 9,000 hours. And basically after the end of that 9,000 hours, the output is dropped to probably about 90%, 80 or 90% of its original output. So what happens with these bulbs is they do gradually fade in output over time, which is why we recommend replacing it about once a year, which works well for that 9,000 number. We make some other lamp systems that could last much longer, 20,000 hours or more. But for these kind of duct units, we're recommending an annual change. Now, if you have an extremely dirty environment, for example, if you're working in a paint shop with paint fumes in the air, well, the lamps are an optical system, and you want to keep them clean of any kind of dirt or real grime that would collect on them. So in that case, we might recommend dusting off the unit occasionally, but in general, what we're designing here is something that can be maintenance free for 1 year.
Okay, thank you. And I do want to jump back. We have time for another question or two. And I do want to jump back, Eric, just for a minute. You had talked about in one of the slides, if you'd like to go there, it's up to you. But you were talking about a product that is coming up that would go in vehicles, buses, corporate shuttles, that kind of thing. And that's interesting. Is there any comment on there in terms of any kind of different considerations there, since it's not in a duct? Or is there any something people should know with that? Because that seems useful.
Yeah, what we're designing is that these can operate, on a car battery, and so we're designing a system now that's gonna have it's pretty large. It's a big UV sort of chamber that gets bolted up to the roof. It's not that heavy, but it's quite long. So it has a long bulb and a long irradiation field, which produces a pretty high UV dose. And basically, it's a retrofit onto existing products. You just take some screws or bolts and bolt it up to the ceiling. And yeah, we're designing it to operate in most US vehicles pretty easily.
Thank you. Thanks. So I guess I'll close it out with one last question, Eric, and that goes around to I'm kind of on the maintenance. I do need to jump back because another question came in on that, and it's talking about filters. And I'm just going to back up and make sure I'm presenting this right. You had talked about filters not being needed with the UV products you've talked about, but then the question came in, what about filters for dust? Filters that would be used normally in an HVAC system. Do you have any comment on how that works? Are they independent of each other, or have you run into that?
UV, it does break down a lot of the filter materials and different kinds of plastics. So if we were to install this into your duct system, we'd want to probably put it in a straight section of the duct system, not next to any of the filters that exist. That said, these lamps are going to treat any of the air that flows through. So if you have a filter at the very end of the airflow line, then this will probably keep the filters cleaner for longer. And there are filters that you could combine with UV to get different kinds of effects. So in general, we wouldn't really say you have to change anything about your current operation to add a UV system to it.
Okay, all right, thank you for clarifying that. Okay, I think that's all the questions that we have time for today. Eric, I want to thank you very much for the presentation, and I see your contact information is there, so I'll let everyone know that they can certainly email you there and also visit your website at soluva.com. So thanks a lot, Eric.
Great, thanks everyone.
And thank you to Heraeus Nobilite for sponsoring this webinar. I would like to let you know that you'll see a quick survey as the webinar closes. It's just a quick one question. Please do take the time to answer that for us on your way out. A recording from today's session will be made available at our website, facilityexecutive.com, and also again on the Heraeus Nobilite website, And you can check that out at saluva.com to learn more about what you've heard today. Thank you, everyone. Have a great afternoon. Bye, Eric.